Okay, so in this equation, we've got barium nitride is reacting with H2O, and this forms barium hydroxide and ammonia. And we've been asked to calculate the mass of ammonia that's produced. Okay, so one of the things we've been told in the question here is that the H2O is in excess, right? What this effectively tells us is that the barium nitride is the limiting reagent. Effectively, it's going to be that determines the amount of NH3 that is going to be produced. And so using that information, rather than approaching it this way, actually, rather than going further in this line of thought, which I'm going to get to all of those parts, but let's look at it from the other side as well. So from an NH3 perspective, we've been asked to calculate the mass, right? And we know that the mass is equal to the number of moles multiplied by the molar mass, okay? Now, this we can work out from the periodic table, but this we can't exactly directly work out from the periodic table. But because of effectively what I've explained, what we can do is use the stoichiometric relationships, which you can see in the equation, this balance equation, effectively reverse engineering it from the barium nitride. We can then work out the number of moles, right? So this is what we're effectively going to do to work this out. So one of the first things in terms of the moles is we don't have actually a number of moles for the barium nitride at the moment, but we do need that to try and progress this question. So how am I going to work that out? Well, we do have a mass. We have a mass for barium nitride here, but we don't have a molar mass. So we could work out. So you know, when you rearrange this, you get that number of moles is equal to the mass divided by the molar mass, right? So let's work out the molar mass. So we can put this to work. So we've got barium here, all right, and we've got nitrogen here, okay, and we need to work out the molar mass of Ba₃N₂. So therefore that is going to be, so MR of Ba₃N₂ is going to be equal to, and so that's, we need the relative, use the relative atomic mass here. So that's going to be 3 times 137.3 plus, so this is the, effectively this is the barium aspect, and then the nitrogen aspect is going to be 2 times 14.0, okay? And so that is going to give us our molar mass. So you can have a go, you know, see what you get, what number you get when you work that out. But what you should find is you get 439.9, okay? And that's going to be grams per mole, okay? Okay, so with that value, we are in a much better position to apply this equation, right? Because now we have the mass, which is given in the question, and we have the molar mass, which we've just calculated. So we can say that the moles of Ba3 Ba₃N₂ is equal to 35.02 divided by 439.9, okay? And that is going to be 0.0796090. Okay, so that's going to be in moles. What I discussed at the start of approaching this question is the fact that the stoichiometric relationship could give us really help us to work out the mass of the ammonia. And this is what I'm going to now explore, right? Effectively, if we look at the ratio Ba₃N₂, the coefficient here is, well, there's no number in front of it, but we can, because of that, we can assume the coefficient is 1, right? The ammonia, on the other hand, which is on the right hand side of the equation, the coefficient is 2, right? So if we articulate that relationship, the molar ratio relationship, what we get is effectively that the N of Ba₃N₂ compared to the N, right, and N being the moles, right, so of NH3 is effectively for every 1 Ba₃N₂, you're going to get 2 NH3, okay? You're going to get 2 NH3. So what does that tell us about NH3? Well, what it tells us on the calculation level is that to get the moles of NH3, it's simply going to be equal to 2 times the moles of Ba₃N₂, which we worked out, right? We've got that value here, so it's going to be equal to 2 times 0.79609, right? And so if you work that out, what you should get is that is going to be equal to it's fine. Yep. So that's going to be 0.159218, right? And that's going to be in moles, right? So moles. Okay, so at this stage, we've got the moles of ammonia. We've been asked to work out the mass of it. So, of course, at this stage, given so we would know that the mass of the NH3 would be equal to the moles, multiplied by the molar mass, right? So it would be equal to the molar mass of NH3 multiplied by this above number, right? So it would be multiplied by 0.159218. But we need to work this out, right? So we need to work that out from the periodic table. So the moles, the molar mass of ammonia, and so we've got nitrogen here, got hydrogen here, and it's NH3, so it's going to be simply 14. So it's going to say MR of NH3. Let's make that actually look like a 3. NH3 is equal to 14, right? Multiplied by 1. I mean, you could choose not to put the 1 there. Plus 1, which is, so this is the nitrogen part, and then plus 1 times 3, right? So H3, right? And so that's going to give you a molar mass of 17, right? And that's going to be in grams per mole, right? So we've got that 17 value, and we just set up the equation where we literally just need to plug that in. So we can effectively do that. So therefore, the mass of NH3 is going to be equal to 17 multiplied by 0.1 2.59218. Okay. So if we do work that out, what you should find that you get is 2.706.706. Okay. Now that's going to be in grams. So we've got a mass value for the NH3. We do need to confirm what the question has asked us to do, right? So it asks us to calculate the mass of NH3 specifically, which is what we've done. But it also asks us to give our answer to a maximum of 2 decimal places, which, looking at our answer, we have not yet done. So we're going to need to round this to 2 decimal places. So it's going to be equal to 2.71 grams. So that's going to be to 2 decimal places. Okay. Right. So yeah, this would be our answer. This would be the mass of NH3, 2.71 grams.